All right, guys, today we're going to talk about section 4.7, which is L'Hopital's rule. And some of you might have found this out on the test. Some of you were trying to use it for the extra credit part. So I know some of you have looked into this, but we know that it's dealing with limits. But it's not extensively dealing with limits. We were so L'Hopital's rule is extensively dealing with limits, but when we studied limits, we didn't study all possible avenues of limits. So this is an application using derivatives that we now know in order to find out limits that exist that were complicated to do that before. For example, if I wanted to find the limit as x approaches 0 of the sine of x over x, then I knew, we've watched this, we did it when we graphed it, right? We know that the sine of x looks something like this. This is the best graph I've ever drawn in my life. And x looks like this. So sine of x over x, when it does that, is like this. Remember, we have this thing that does this thing, and then it kind of slows out. Now it looks like I just scribbled. I promise I did it. So there we go. It doesn't like when I do that, I guess. I guess if I do that, does it just delete it? No. We're learning together, guys. It's okay. So we know that this limit exists based on what we've done before with graphing and looking at it from both sides. But if I plug in 0, like we can with polynomials, then you're going to see that we get the sine of 0 over 0, which gives us this form of 0 over 0, which we can't do anything with. It doesn't help us because I'm dividing by 0. So what people who are smarter than I did before, they came up with a way that we can evaluate this. Because we know, let's say that we want to find the limit as x approaches a of f of x divided by g of x, which we get as 0 over 0, which gives us this, f of x, f of a equals g of a, which equals 0. Well, we can do a little trick and say, well, what if I took the derivative of these? So that's going to be this f of x minus f of a all over, as x approaches a, x minus a, divided by the limit as x goes to a of g of x minus g of a all over x minus a. Now this, if I wanted to write this, this is the definition of what is the limit. This is the f prime of x over g prime of x. Okay? Well, this just equals, I know that x minus a divided by x minus a is just, they cancel out. So if I invert and multiply, if you wanted to do that, we still have the limit as x approaches a of f of x minus f of a all over, g of x minus g of a. But up here, we know that f of x equals g of x, or f of a equals g of a, which equals 0, which gives us this limit as x approaches a of f of x over g of x. And you're like, well, that's what we started out right here. The answer is yes. And that's kind of what we wanted, because if we have this form where f of a and g of a equals 0, then it's equal, the derivative is equal to the same thing. Okay, let's come up with a geometric example to show you here. So if we look at this right here, we see this is some function g of x, this is some function f of x, and as it approaches a, they both cross 0. And so the derivatives of their tangent lines at those points, they are the same thing. So that the slope of the tangent, so like you have this derivative divided by this derivative at A, you can see the derivatives are the same thing at A as the functions are because of how this is located. So the derivatives will work, meaning that if I come back here to my first example, I want to find the limit. Oh, let's go down here. As x approaches 0 of sine of x over x, I do L'Hopital's rule and say, well, this is the limit as x approaches 0 of cosine x over 1, which is the derivative of the top and the derivative of the bottom. Notice I did not use the quotient rule. If you use the quotient rule, that's like the number one mistake with L'Hopital's rule. Don't do that. That's not what we're talking about. And the cosine of 0 is just 1 over 1, which equals 1, which we have proved earlier, saying like, hey, guess what? We can just do L'Hopital's rule. So we know L'Hopital's rule is going to work if the limit as x goes to a of f of x over g of x equals 0 over 0. Now this is going to work if it's x goes to a, if x goes to a from the right side, if x goes to a from the left side, if x goes to infinity, if x goes to negative infinity. As long as we get this 0 over 0 in determinant form right here, boom, we got it. We can use L'Hopital's rule. But what about the indeterminate form, let's say infinity divided by infinity? Now, the proof of this, you're going to prove if you have to take real analysis. So we're actually not going to go into that. But you can trust me when I say, hey, it works too. If you get the indeterminate form of infinity over infinity, okay, plus or minus infinity over plus or minus infinity, then you do the same thing. Now, notice we have these forms out. Like, what about if it's like 0 over infinity? No, not good. Infinity divided by 0, also not good. They need to be the same. So we got a 0 over 0 or some combination of infinity over infinity. And you can use L'Hopital's rule to determine these limits and how they exist using our other limit rules. You'll hear people call it L'Hospital's rule because it's how you spell L'Hopital, just minus the S. But it's L'Hopital is how we say that, and that would be great. Good luck on your questions today. You can use L'Hopital's rule more than once, meaning if I take the limit, I take the derivative, and I get 0 over 0 again, I can take the second derivative of each one until I get a number. Okay. And so L'Hopital's rule is great, and I'm sure you'll have a great time doing it too.